Welcome to the YesDev channel and the Code Wars series, where we solve katas from the Code Wars website in Rust for fun. So let's get to it. Today's kata is called Directions Reduction. And I will not completely read out the introduction text here. The link will be in the description if you want to check it out. But the quintessence of this task is that we get an array or a slice with directions inside the slice. And what we have to do is we have to reduce the directions that are opposite of one another. So north and south can be removed as they are just opposites of one another, and east and west can be removed. So in the story of this task, we would have to go east and then directly go west, and so that wouldn't make sense. So we reduce these instructions. And then here is an interesting case because we removed north and south, we removed east and west, and now south and north are again next to each other. And these are also opposite directions, so we have to remove them as well. And the last thing we are left with is west. And that's the entire task. There are more examples here and full description of the problem. But I think this sums up what is needed to know. And let's get over to our whiteboard first and look at a little example and get a better mental image of what we need to do. So here we have our first case. This is just copied from the description of the kata. And so how can we approach this? To find out whether we can cross out anything, we can use two pointers, where the first points to north and the second points to south, or in a more general case, to the first and the second position. Then we check whether they are opposite directions, and in this case, this is true, so we can cross both out. And here our pointers still point to the same positions, as we didn't move them, and we cannot move them further back in this case. So now we check, are these two opposite directions? And in this case, they aren't. So we move both pointers 1 point forward. Now we also check if those two are opposite directions, and in this case they are. So we cross those out again. And in this case, we now need to backtrack because the pointers are now pointing one position too far into the array. We also have to check the beginning again, as now south has a different neighbor and south and north could now be opposite directions. So now that we've moved the pointers back, we check again, are those opposite directions? And as this is true, we also cross them out here. And now we are only left with one element, and we cannot check that element against anything else. So we know we are done and the algorithm is complete. And this is actually the solution we want to arrive at. Let's get over to Visual Studio Code and see how we can implement this in Rust. Now back in Visual Studio Code. Up here we have our direction enum with the directions northeast, west, and south. And we have some derived traits up here: clone, copy, debug, partial equality, and equality. And down here we have our tests, and here in the middle we have the actual function we want to implement. Now to implement our solution, in the example I showed on the whiteboard, we used a mutable data structure. And in this case here, we just have slice. So we cannot mutate it, or we cannot mutate how many positions are in it. So we should use a vector. So let's redefine this array as a mutable variable and say array.toVec. And now we have redefined the array as a vector. And let's also just put the array down here or the vector done here, so that we have a return value. Now, to use the pointers we had in our example, we can simply use a mutable index and set it to 0 and use a while loop to iterate over our array and just check that our array length is greater than 1, because if we only have one element, then we cannot check against anything else. And additionally, we need the index to be smaller than our array length -1. And the -1 comes from the fact that we have to check 2 elements in each iterations. So our index should be the last index. Now, what we want to check is whether or not we can keep the value we currently have, or if we should remove it. To do that, we check against the array at our index and the array at index +1. And here we can use a match statement and match against the tuple we have here. So we can check that the array at this index is, for example, direction north and direction south. And then we can say, okay, in this case, we want to actually keep the value. No, we want to drop the value that we have. Let me quickly fill out the other cases for the directions. Now that we have filled them out, these are just the cases in which we want to drop our elements. So when we think about it, in our example on the whiteboard, we simply remove the elements, and we can do the same thing here. We can simply say array remove, and then we can pass in the index. And for the first element, it's obviously index, what we have to remove. But for the second element, it is also index. And that is because if we remove the first element, the second element goes to the same place as the first element was. If we add 1 here, we remove a different element, and have to keep that in mind that we don't do that, because that could lead to a bug that's hard to detect. Now that we have implemented that, we have to think about how many places our index has to go forward or backward after we did this. And if we remember the whiteboard, we went back 1 position after we did this, in all cases except when we were at the beginning. So when our index was already 0. And in Rust, we can simply do that by saying subtract saturated, or saturated sub in this case, and then sub by 1. As a quick insert, what does saturating sub actually do? In the documentation, it says saturating integer subtraction computes self minus right-hand side, saturating at the numeric bounds instead of overflowing. And what that means is it actually stops at the bounds. So if we would have an overflow, it just stops at the maximum value. And if we would have an underflow, then it would stop at the minimum value. You can see that here with the usize, if we sub 127, it goes around to 0. So it just stops there. This is an equality assertion. And yeah, that is actually exactly what we want. We just want to stop at 0 in our case. So saturating sub is perfect for us. So now that we have this case and our index is matching what we actually want to do, we can now do the else branch, or better said, the any case with our match. And in any other case that this is not one of these combination, we simply want to move our index 1 place ahead. And in this case, we don't have to check if it's an overflow, because the usize won't overflow when we use addition here, as the array won't be greater, or nearly as great as the maximum value of usize. So now one thing I forgot is that we have to actually assign the return value from the saturating subtraction. Otherwise, the value will just land nowhere, and our index won't be changed by this operation. So now that this is done, our algorithm is complete as we remove in the cases where we want to remove an item and then move the pointer back if necessary. And otherwise, we simply go ahead one place, and this will always check all positions as we wanted in our example. And so let's run the tests and check if this actually works. And as we can see, this works perfectly. And yeah, then let's take this code and put it into CodeWars. So now in CodeWars, we have our solution, and let's attempt it. And this concludes the first part of this kata. This kata can be seen as complete. The solution is completely valid and completely done on its own. But there's a second part of this video where I implemented another solution to that problem and also discussed some other solutions. Hope I will see you there.